We now discuss about relative density of a substance. Relative density previously was also called as specific gravity, but this name is nowadays not used, but it was also called as specific gravity. But we will use the term relative density, which is abbreviated as RD. So the relative density of any substance is its density in comparison with the density of water. The density of water is maximum at 4 degrees centigrade, and in CGS unit the density of water at 4 degrees centigrade is 1 gram per centimeter cube, and in SI units at 4 degrees centigrade the density of water is 1000 kg per meter cube. So relative density is the density of any substance divided by the density of water at 4 degrees centigrade. At 4 degrees centigrade, because at 4 degrees centigrade the density of water is maximum. Remember, at 4 degrees centigrade density of water H2O or water is 1 gram per centimeter cube, or in SI units this is 1000 kg per meter cube. Now, density of any substance is also equal to mass by volume of that given substance. So, if you consider a unit volume of the substance, that means if you consider 1 centimeter cube of the given substance, then you can say that the mass is equal to the density. You know that density, let me denote density by rho. Density is mass by volume. So if you take unit volume, or suppose you take 1 centimeter cube of the volume of the substance, then its density is equal to mass. That means if your volume is 1 centimeter cube, then you can say that density is equal to the mass. So instead of density, we can say that this is the mass of unit volume of the substance. Mass of unit volume, by unit we mean 1 of the substance, divided by, obviously in case of density of water also, you should now say mass of unit volume of water, provided the volume of water is 1 centimeter cube, unit volume of water. Obviously the temperature remains the same, that is 4 degrees centigrade, because at 4 degrees centigrade the density of water is maximum. Now, because this is the ratio, we can divide mass by any volume. Suppose you take 100 centimeter cube of the substance and 100 centimeter cube of water, so the volume will cancel out. So the ratio of mass of unit volume will be the ratio of mass of any volume of the substance. So this, now you can say mass of any volume, let that any volume be denoted as V centimeter cube. Mass of V centimeter cube of the substance, because you are considering the same volume of the substance and the same volume of water. So this can be written as mass of V centimeter cube of the substance. We can have any value. Mass of V centimeter cube of water at 4 degrees centigrade. So relative density is a ratio of density, it also a ratio of mass. Now this substance, I mean any substance, can have any density value in comparison with water whose density is either 1 gram per centimeter cube or 1000 kg per meter cube. So, because it is the ratio of two similar quantities, either it is ratio of density or ratio of masses, relative density has no unit. Relative density is purely dimensionless quantity. It has no units, and so it is called as dimensionless quantity. It is a pure number. Relative density is a pure number. It has no dimensions. It is a dimensionless quantity. And so it has no units. It has no unit. However, density has a unit, mass has a unit, and volume has a unit. Now, as you know that the density of water at 4 degrees centigrade in CGS unit is 1 gram per centimeter cube, and that in SI unit is 1000 kg per meter cube. So, if you know the relative density of any substance, you can just multiply by 1 gram per centimeter cube and express that density in CGS unit, or you can multiply by 1000 kg per meter cube and express the density in SI unit. So you can say that in SI unit, density of any substance, let me call it as rho, density of any substance is equal to relative density into 1000 if we express the density in kg per meter cube. If we express the density in CGS, it is just RD into 1, means simply RD, and just you have to add the unit gram per centimeter cube. This is because density of water is 1 gram per centimeter cube in a CGS unit and 1000 kg per meter cube in SI unit. Suppose we try to measure the relative density of a liquid using a density bottle. Using density bottle. I have already discussed what is density bottle and how we can measure the density of any substance using density bottle. So this density bottle can be also used to measure the relative density of a liquid. In the first step, we take an empty dry density bottle and then find its mass. So you can say there is a dry empty density bottle and its mass is measured using a beam balance, and let the mass of that empty dry density bottle is m1. So mass of empty, obviously it is dry, density bottle is suppose m1, and this mass has been measured using beam balance, which is available in the laboratory. And suppose you measure the mass in grams, so it is suppose m1 gram. Then we fill the density bottle completely with water and properly insert the stopper. The excess water will definitely overflow through the hole that is present within the stopper, and then properly dry the outer surface of that bottle using blotting paper, and then we again measure the mass of the bottle with water inside it using a beam balance. And suppose that mass is m2 grams. So mass of bottle, that is the density bottle, plus water within it. It is also measured using a beam balance, and mass of empty density bottle with water inside it is M2 gram. Now we again empty the density bottle, we dry it properly, and now fill the empty density bottle with the given liquid, whatever the liquid is. Suppose the liquid is glycerin. So any type of liquid can be taken whose relative density we are trying to measure. So now we again empty the bottle, dry it properly, fill the given liquid, insert the stopper. Excess liquid will definitely flow through the hole in the stopper, and we will dry its outer surface using blotting paper, and then again measure the mass with the liquid inside it. Suppose the mass is now M3 gram. So what we get is mass of the density bottle with the liquid inside it. This is again measured using a beam balance, and suppose the mass is M3 gram. So from these two results you can say that mass of water is obviously M2 minus M1, because bottle plus water is M2 and empty bottle is M1. So mass of water is obviously M2 minus M1 in gram. Similarly, if you subtract M3 minus M1, you will get the mass of the liquid, that is M3 minus M1. Why? Because mass of bottle plus liquid is M3 and mass of empty bottle is just M1. So M3 minus M1, you will get the mass of the liquid. Now, as we have already defined, the relative density is equal to mass of a given volume of the liquid divided by mass of a given volume of the water. Now in this case the volume is same because the density bottle remains the same. The volume of the liquid inside the density bottle and the volume of water inside the density bottle is the same. So just if we divide the mass of the liquid by mass of water, we will get the relative density of the liquid. So you can say relative density of the liquid is obviously mass of the liquid by mass of water of an equal volume of water, and here obviously the volume is equal because we haven't changed the density bottle. It is the same density bottle that we are using while performing the experiment. Mass of an equal volume of water, H2O. So hence you can say that the RD of the liquid is simply M3 minus M1 divided by M2 minus M1. This is a very easy technique to calculate the relative density of a unknown liquid. Our next topic is flotation. So we shall study about principle of flotation and what helps a body to float on the surface of a liquid and related concepts. Before discussing about the principle of flotation, you might all know that if you place a paper boat or a cork on the surface of water, it floats easily. But if you place an iron nail or a spherical metal ball on the surface of water, it will definitely sink. So flotation and sinking are concepts associated with the density of the substance and the density of the liquid. It is a very common observation that if the density of the material is greater than the density of the liquid, then that substance will definitely sink in the liquid. For example, iron nail will sink if it is placed on the surface of water because the density of iron is definitely greater than that of water. Whereas if the density of a substance is less as compared to the liquid, then that substance will float on the surface of the liquid. For example, a paper boat or a cork whose density is much less than that of water floats on the surface of water. So while studying the principle of rotation, we should realize what happens or what are the forces that act on a body when it is immersed in a liquid. So suppose a body is immersed in a liquid and two forces act on it. Immersed in a liquid. Now, when you say that it is immersed in a liquid, it is either totally immersed or it is partially immersed. It depends upon how it will float. That is a different characteristic of flotation. But presently, if a body is partially immersed or wholly immersed in a liquid, then two forces act on it. The forces that act on it is the weight of the body, which acts vertically downwards. Suppose the weight of the body is denoted by capital W, and this weight of the body is the pull exerted by earth, that is the gravitational pull. Weight means the gravitational pull exerted by the earth. So the weight of the body will act vertically downwards. And the second force that acts on the body is the force exerted by the liquid, that is called as the upthrust or the buoyant force. Now this buoyant force is actually the force which helps in the flotation of the body. So the buoyant force or upthrust, let me denote it as FB. F means force and B represents buoyancy, so it is denoted as FB. So the buoyant force or the upthrust is exerted by the liquid in the vertically upwards direction. Vertically upwards. Now whether the body will float or whether the body will sink, it depends upon the net force acting on the body. So we have to analyze three different cases. The first case is if the weight of the body is greater than the buoyant force. If the weight of the body is greater than the buoyant force. So in that case, the resultant force or the net force acting, the resultant force will be the greater force minus the smaller force. And the direction of the resultant force is in the vertically downward direction. Because if you observe that W is in the vertically downward direction, whereas upthrust or buoyant force is in the vertically upward direction. So if weight is greater than the buoyant force, that means the net force or the resultant force is acting along the vertically downward direction, and that will allow the body to sink. The body will sink. The body sinks. Now it generally happens when the density of the solid is greater than the density of the liquid. It happens when, in most of the situation this is true, it happens when density of the solid is greater than density of the liquid, and as a result the body definitely sinks within the liquid. it does not float again. In cases, the weight of the body is equal to the upthrust. The weight of the body acting vertically downwards is equal to the upthrust or the buoyant force exerted by the liquid acting vertically upward. In this case, you can say the resultant force acting on the solid, which is 0. The resultant force acting on the solid is 0. It also means the apparent weight is 0. Apparent weight is 0. Now, real weight or actual weight is the weight of the body in air, and apparent weight is the weight of the body in the liquid, that is the actual weight minus the upthrust. Because here actual weight and upthrust are both equal, the resultant force is 0, and we say that the apparent weight is also 0. Hence you can say that the apparent weight of a floating body is 0. So in this situation, the body floats. The solid which has been placed on the surface of the liquid floats. In the previous case where W was greater than Fb, the body sunk to the bottom of the liquid. But in this situation, the body floats, but it floats inside the surface of the liquid. Inside the surface of the liquid. And this generally happens when the density of the solid is equal to the density of the liquid. It happens when density of the solid is equal to the density of the liquid. And the third case is the weight acting vertically downwards is less than the upthrust. In this case also the body will float, and in this case the resultant force is acting in the vertically upward direction. The resultant force will be the greater force minus the smaller force. Here upthrust is the greater force, so Fv minus W, and the resultant force will act in the vertically upward direction. So in this case also the apparent weight is 0. Now apparent weight 0, we don't confuse it with the previous case where the resultant force was W minus Fb and W was equal to Fb. Apparent weight actually means the weight inside the liquid, which is equal to the weight minus upthrust. So in the apparent weight is in the vertically upward direction, and apparent weight of floating body is always taken to be 0. Okay. Now the body definitely floats, but with maximum of its volume outside the liquid. A portion is inside the liquid and a portion is outside the liquid. So in this case we will say that that much portion of the body is immersed. Remember that the solid body is partially outside the surface of the liquid and it is partially inside. So what it then definitely means what amount is inside and what amount is outside actually. So that much portion of the body is immersed, by which the weight of the liquid displaced becomes equal to the weight of the body. By which the weight of displaced liquid that much portion of the body is immersed by which the weight of the displaced liquid becomes equal to the weight of the body. Weight of the body. And in that sense only the apparent weight is 0. Don't confuse with the previous case where I said that apparent weight is 0 because W equal to F3. In this case the apparent weight is 0 because a portion of the body is immersed and the immersed portion is equal to weight of the displaced liquid. In that sense the apparent weight is 0. So a portion is inside and a portion is outside. So in this case also the body is floating. Obviously the body floats. A portion is inside and a portion is outside. The portion of the solid that is inside the liquid, weight of that portion is equal to weight of the displaced liquid. But this we can, the three cases we can demonstrate by the help of a diagram also. So a diagrammatic presentation of all the three cases that we have analyzed. Suppose rho S means density of liquid, rho S means density of solid, and rho L means density of the liquid. W represents weight of the body. Weight of the body means weight in air, and Fb means the thrust exerted by the liquid in the vertically upward direction. So in this first case, the body is shown to sunk to the bottom of the liquid. Now, if you remember, in this case, we had weight greater than upthrust, and so the body sunk to the bottom of the liquid. And in this situation, in most of the cases, the density of the solid is greater than the density of the liquid. The second case, the body floats with the entire volume of the body inside the liquid. Here, the weight of the body is equal to the upthrust, and generally the density of the solid and the density of the liquid are the same. And apparent weight is 0. Because whenever a body floats, its apparent weight is 0. In this situation and this situation, the body is floating. And in both the situations, the apparent weight has to be 0. In this third case, the upthrust is more than the weight of the body, as a result of which a portion is outside and a portion is inside. In this case, in general situations, we observe that the density of the solid is less than the density of the liquid, but just remember that the portion inside, the portion that is inside the solid, inside the liquid, weight of that portion inside the liquid is equal to the weight of the displaced liquid, and so apparent weight is 0. So in this case also the apparent weight is 0. And that is why I have said that much portion of the body will get immersed, by which the weight of displaced liquid becomes equal to the weight of the body. So actually, in this situation, the entire volume of the solid is equal to the amount of liquid displaced. But in this case, a portion is outside and a portion is inside. So the portion that is inside is only responsible for displacing the amount of liquid. And that is why in this case the apparent weight is 0, because a portion which gets immersed, or that portion which is inside the liquid, and weight of displaced liquid becomes equal to the weight of the body. And that is why the apparent weight is 0. So these are the three situations. So the first situation the body sinks, and in the second and the third situation the body floats. But in the second situation the entire body is immersed inside the liquid and it is floating, and in third case a portion is outside and a portion is inside and it is floating. Remember that these two cases represent flotation, and the first case represents the situation where the body sinks to the bottom. In the second and the third case, the apparent weight is 0. Second case, weight is equal to upthrust. Third case, upthrust is greater than weight. In the second case, in most general cases, the density of solid and liquid happen to be equal, and density of solid is less than density of liquid in the third case. So this is the situation that represents flotation. So now we can say that by the principle of flotation, the weight of floating body is equal to the weight of the liquid displaced by its submerged portion. So finally you can say that the principle of flotation, briefly, it says that weight of floating body is equal to weight of liquid displaced by the immersed portion of the liquid. Weight of liquid displaced by the submerged part or what I have said as immersed portion. Now this is the principle of flotation. So you can say that apparent weight of a body is equal to its true weight minus upthrust or buoyant force, and by true weight is the weight in air, you can say, what we have denoted weight in air or true weight as W and the upthrust as Fb. And for a floating body, the apparent weight is 0. Now this is directly from the principle of flotation or law of flotation, whatever you say. So according to the principle of flotation, when a body floats in a liquid, the weight of the body is equal to the weight of the liquid displaced by the immersed portion of the body. And then the upthrust is equal to the weight of the body, as a result of which the apparent weight is 0. So we say that apparent weight of floating body is 0. Remember that weight of the body is equal to weight of the liquid displaced by the immersed portion of the body. That is the principle of flotation, and for floating body the apparent weight becomes 0. Now we can show mathematically what portion remains immersed inside the liquid and what portion remains outside the liquid. Suppose, let me denote small v as immersed volume of the solid. That means the volume of the solid inside the liquid. Immersed volume of solid, which is volume of solid inside the liquid. Volume inside, or volume of solid inside the liquid, and let capital V denote the total volume of the solid. That is the volume inside plus volume outside, total volume, which is volume inside the liquid plus volume outside the liquid. And rho S, suppose it is the density of the solid, and rho L is suppose it is the density of liquid. So we'll apply the principle of rotation in order to obtain a relationship between all these quantities. So by the principle of rotation, weight of liquid displaced is equal to weight of the entire solid the body, or weight of the solid, you can say. Now remember that small v portion of the solid is inside the liquid, so the volume of liquid displaced into the density will be the mass, and that if you multiply with the acceleration due to gravity, it will produce weight. So weight means mass into acceleration due to gravity, weight of liquid displaced. So as small v is immersed inside the liquid, that volume of liquid will get displaced. So small v into density of liquid, this is the mass of liquid displaced. If we multiply with g, we get weight of liquid displaced. And weight of the body means the entire volume of the body into its density. This gives you the mass of the body, and if you multiply with the acceleration due to gravity, that is g, we get the entire weight. So obviously you can see that g cancels out from both the sides, and so small v by capital V is equal to density of solid by density of liquid. So you can say that volume immersed by total volume is equal to density of solid by density of liquid. Volume immersed by total volume is equal to density of solid by density of liquid. So this you can remember. As an example, if you consider the density of a solid is suppose 3/4, and suppose 3/4 of it is immersed in water and 1/4 of it is outside water. So if there is a cubical volume of a substance, and suppose the density of that material is 0.9, so you can say that 90% of the volume of that material will get immersed in water and 10% will be outside the surface of water. So if you know the density of the solid and the density of the liquid, you can predict what portion is in. We can predict the volume, the portion of the volume inside the liquid and the portion of the volume of the solid outside the liquid. So there are different applications of the principle of rotation. Say for example, it is a common observation that if you place an iron nail on the surface of water, it will definitely sink. But iron ship floats in water. Now the flotation of iron ship cannot be expressed on the basis of that density of iron versus the density of water. Obviously, the density of iron is greater than the density of water, whether it is river water or sea water, and definitely on that basis you can say that any object or any substance that contains iron will definitely sink. But this is not so in this case. Iron nail sinks whereas iron ship floats. Now this is because the ships that are made up of iron generally are hollow, and the empty space contains air, which makes the average density of the ship less than that of water. So remember that because of the shape of the ship, is such average density of the ship is less than density of water, and that is the reason why the ship will float on the surface of water. Now that special type of shape is also called as streamline shape. On the other hand, you can consider the flotation of a man. It is easier for a person to float in or swim in sea water rather than swimming in river water, because sea water contains dissolved salt. As a result of the dissolved salts in sea water, the density is much more than the density of river water, and the weight of the man gets balanced by the less immersed portion of his body in sea water as compared to that of river water. So it is easier to swim in sea water than in river water. Similarly, if you consider the flotation of ice cube in that of water, so if ice cube floats in water, then 9/10th portion of that ice cube is inside water. Almost, you can say, on an approximate basis I am saying that 9/10th portion of the ice cube is inside water, and 1/10th portion is outside water. So the maximum portion remains inside water and the minimum portion remains outside water. Now this is the reason why I am saying 9/10. I am assuming that the density of ice is nearly 0.9 gram per centimeter cube, and density of water, let me assume it as 1 gram per centimeter cube. So if you compare this relationship, small v by capital V, density of solid by density of liquid, so density of solid is here density of ice, that is 0.9 by 1, which means 9/10. So you can say that 9/10 portion of ice is inside water and 1/10 portion will be outside water. So there are several such examples where you can apply the principle of flotation. If you consider icebergs or glaciers floating on sea water, then those icebergs and glaciers are definitely dangerous for ships, because most of the portion of the iceberg is inside sea water and a very small portion is outside water, and hence that little portion is only directly viewed from the ship, and it becomes difficult to resist any type of collision with the iceberg, because most of the volume of the iceberg is inside water. If you compare, suppose the surface of sea water, and if there is an iceberg, then almost you can say that the maximum portion is inside and a very small portion is outside the seawater. Ice. A small portion of the iceberg is outside seawater. If you consider the flotation of a submarine, then you will realize that a submarine floats inside seawater, and on requirement it can also come outside the seawater. This is because a submarine is provided with special type of tanks which are called as ballast tanks. We can also call them water tanks. So submarines have special type of tanks which are called as water tanks inside. when the submarine wants to dive inside water, these tanks are filled with water, and so the average density of the submarine becomes greater than the average density of seawater, and it sinks. When submarine dives in seawater, then water tanks are filled with water, get filled with water, and so the average density of the submarine now becomes greater than density of seawater, and so it sinks. And when the submarine wants to come to the surface, these tanks are emptied out, and that makes the average density of submarine less than the density of seawater, and it rises up to the surface of the water. So when your submarine wants to come to the surface, the water tanks are emptied. When the water tanks are emptied, the average density of the submarine will become less than the density of seawater, and it will help the submarine to float or come up to the surface of water. So these tanks are also called as ballast tanks. So there are plenty of such examples where you can apply the principle of flotation and realize how a body floats depending on its density, depending on the upthrust and related phenomena. Similarly, if you consider the flotation of whales also work much like whales also actually dive into seawater or come to the surface, much like the principle that is applied to submarines. So a whale can sink or rise to the surface of seawater because they have a special organ in their body which is called as swim bladder. So the whales possess swim bladder. Now this swim bladder can hold air, and in order to come to the surface of water, the swim bladders are filled with air, and that makes the average density of the whale less than that of the water, and so the whale can come up to the surface of water. Whenever the whale wishes to dig or dive deep into the water, then they will empty the swim bladder, and this will increase their average density, and then they will sink into the water. Similar application of flotation is also in the case of balloons. So generally, if you observe that a hydrogen or helium filled balloon, rises in air. This is because the density of hydrogen or helium is much less than the density of air. So since the density of hydrogen or helium is much less than density of air. And that is why if a balloon is filled with hydrogen or helium, it will definitely rise in air. And as a result of which the buoyant force that the balloons will experience becomes much greater than the weight of the balloon. The buoyant force or the upthrust on the balloon is much greater than the weight of the balloon itself. Buoyant force is exerted by air because whenever the balloon is floating on air, it is actually displacing air. So the buoyant force or the upthrust exerted by air on balloon is greater than the weight of the balloon itself. As a result, the balloon will rise up under the influence of the net upward force. So there are many such examples of flotation. You can refer to any standard textbook